What is up, everybody? Tom McGraw here with another episode of our Learn Rust Live series. If you're watching live on Twitch, use that chat, ask questions, get involved. If you're watching on YouTube, put some stuff in the comments. Just want to give a shout out to everyone on YouTube who's been subscribing, following, watching the videos. It's been awesome to see, especially for me, since I'm just taking my stream that I'm doing every Tuesday, 9 p.m. to 11 p.m., and uploading it. So it's been easy for me, little to low, no editing, right? I just cut out the intro in the beginning, but yeah, really awesome to see, and I really appreciate it. And I've been talking about this for a while, putting out some more one-off content for YouTube, and I'm definitely gonna be trying to do that because I've been getting the love from YouTube. Love to see that. So more coming your way. Don't worry, we'll be getting some good stuff. I got some good stuff lined up. I've just been trying to figure out in what order to do things. I have some non-Rust material, so I want to kind of sprinkle that in, but I also want to get some Rust material out because that's what you've all been joining and viewing for. So awesome to see that. Keep it up. And hey, if you're ever around for the live stream, 9 p.m. to 11 p.m., we got Albert in the chat tonight. Why not live stream on YouTube too? I actually will be doing that. So I currently use Streamlabs. Shout out to Streamlabs for creating some amazing software. And I will be getting a Streamlabs Pro subscription, which will allow me to simulcast to both YouTube and Twitch. So that is coming. I'm excited for that as well. But yeah, wanted to grow that Twitch kind of organically and see how that worked out. But YouTube's been pretty good. I like it. So awesome. I'm glad everyone's enjoying it. So tonight, where we at? We're going to be doing chapter 16 of the Rust programming language book. We started it last Tuesday. We finished chapter 15, started 16, started learning about threads. And let me tell you, this is a piece of Rust that I've been really looking forward to. Coming from other language where concurrency and asynchronicity is a thing, it's been really exciting to see how Rust takes that approach. You probably have heard me say many times, I'm a huge fan of the language Elixir. In fact, Albert in the chat and I have been working on an Elixir project. More to come on that. But it's a really fun language that makes concurrency really easy. So it's something I've been excited about recently. And now being able to dive into Rust and learn that has been awesome as well. You may also remember that we did Rustling's exercise and we had to skip the chapter on threads because we just didn't know what the hell we were doing. Or at least I didn't, right? Some people in the chat were like, oh, Tom. We had some pro genius IQs in the chat contributing. Shout out to that for helping me out there, but we ended up skipping it. We got Dozeboy in the chat. What it is. Welcome, Dozeboy. Happy to have you here. But all right, so before we get started, I got to give the usual plugs. So we got the YouTube channel. If you've missed any of the many videos, you can see we have 21, right, in just this series. Check it out here on YouTube. You can watch it at your own pace, 2x speed. I've been getting comments saying that people have been enjoying watching it at 2x speed, so I sound like a chipmunk, but it's a little sped up. You can shrink that 2 hours into 1 hour, which is fantastic. Check that out. We got the videos from chapters 1 all the way to 15, and then in the middle here, we took a break to do Rustlings. Those are the exercises, the Rust exercises, so we could flex those muscles that we've been building up, right, while we've been going through the book. Also, video here on building a Rust dev environment using Docker. So if you're not fully committed to Rust, don't want to install it on all your machines, but you want a repeatable development environment, check out that video. It's going to show you how to set that up with Docker. All you need is to have Docker installed. It's pretty easy. And in the past, we've done other stuff. We built a serverless API using AWS Lambda. Really great technology for getting started on backend. You don't have to manage your own server. So we did that with Node.js using TypeScript. We backed it with a Dynamo database and used S3 for file storage. And we did that in a 2-hour session, but really fun. And then before that, we did a little React Native stuff. We'll probably return to that as well. It's an area where I'm particularly comfortable. So more to come. I know I've been saying it, but yes, more one-off content to come for those watching on YouTube. I do appreciate it. So check that out. Follow on Twitter. You'll get posts. You can see you get posts when I go live, as well as any other content that I tweet. I also follow some awesome people, so you'll see some of their stuff come up as well. And then everything we do here live on all these videos gets posted to GitHub. It's all public, right? It's all sharing. So the current repo that we're working out of is this Learn Rust Live repo, where we have all the chapters we've been going through. You can see I posted last week's already. Pull that down if you want to look through the code, or get a repo going yourself, or just follow along. It doesn't matter, but it's there for you if you need it, if you want to reference something. It's there for me if I need to reference something, right? And as always, if you've been watching these videos, you know where we're going next. We always got to give a shout out to the authors. Steve Klobnik, Carol Nichols, and anyone from the Rust community that's contributed to this fantastic book. We couldn't be here doing this without those contributions. It's been fantastic. I mean, the quality of content that they put out for free is unbelievable. I've tried many different languages. A lot of them have great content. I'm going to give a shout out to Elm, right? Elm put out fantastic documentation. JavaScript's kind of all over the place, but Rust is here. It's made it easy and accessible for new people to come along and read, and for me to do what I'm doing here today. So again, shout out Steve Klobnik, Carol Nichols, and anyone from the Rust community that's contributed to this, because I'm sure there have been a lot of contributions. But today, we're going to pick it up on chapter 16. So let's dive right in, right? Where do we leave off? Let's go do a quick recap of where we left off. So we learned about the basics of threads. And I'm going to put this over here so I can pull up my code here. So we started out with, let's do this full screen for a second. We started out with threads. We learned how to spawn a thread. So we spawned a thread that counted from 1 to 10 and slept a few milliseconds in between. We spawned a second thread and we joined them and unwrapped them. And we saw the order that we got things, right? And the order is not repeatable, right? Because the threads they run concurrently. So whichever one gets to that output first, it's not a guaranteed printing order, but it's going to give us concurrent. So it's going to happen all at the same time. So we did that. We did another one where we joined up here and saw one spit out all of its stuff before seeing the second one. That was pretty cool. And then we saw using move closures with threads. So the move closure was used alongside thread spawn because it allows you to use data from one thread in another thread. So we have this vector here. We spawned a new thread where we said, here's a vector, and printed it out. You can see here we have this handle, thread spawn. We had some issues. It told us to add move. So we added move so that we could take ownership of the vector, because you need to take ownership of the vector. We took ownership of it so we can print it. And then we talked about sharing state between two threads. And the way to do that was message passing. And the description that they used is, you can imagine message passing. Well, first of all, it has 2 points, right? It has a transmitter and a receiver. And you can think of the transmitters as the upstream, right? All these things that feed into the stream, right? And the receiver is the one thing at the end that receives it all. So all these branches end in one spot. So you can have many transmitters, but you only have one receiver. And we actually spun up our own. I'm going to scroll down to the bottom here. So we got our own going here, where we initialize a channel that gives us, we destructure it into the transmitter and the receiver. We create a first transmitter by cloning the transmitter. And then we spawned a thread that just printed out a few different things and slept for 1 second. We then spawned a second thread. And for that second thread, so you can see for the first thread, we use tx1. We use tx1.send. That's going to be the first transmitter. And for the second thread, we use the original tx to send. And then we capture that all with our receiver, rx, which again came from the instantiation of this channel. So that was a way to have multiple threads being consumed in a single place. So pretty interesting to see that here. All right. So let's check out where we ended, and we'll jump right into the next part. So it says here, you might see the values in any order depending on your system. This is what makes concurrency interesting as well as difficult, right? If you experiment with thread sleep, giving it various values in the different threads, each run will be more non-deterministic and create different output each time. So this is where we're starting now. Now that we've looked at how channels work, let's look at a different method of concurrency. All right, so let's dive in. So we're gonna go over here. We're gonna learn about shared state concurrency, and I'll keep this open in here in case we wanna write some code. We'll just spin up another repo. Yeah, we're gonna be using Mutex. So what I'll do is I'll create that now, just so we're ahead of the game. So we have message passing. I'm gonna go up a level, and I'm just gonna do cargo new Mutex. We'll go into Mutex, and we'll just open that up. All right, so now we got a fresh spot to start up to work with Mutex. We got our nice new main function, and we'll be able to go from there. All right, shared state concurrency. Message passing is a fine way of handling concurrency, but it's not the only one. Consider this part of the slogan from the Go language documentation again. So we learned about this slogan last time. Let's consider it again. Do not communicate by sharing memory. Wow. What a profound statement. Do not communicate by sharing memory. What does that mean? It's meaning there's other ways to communicate. Don't communicate by sharing a resource, meaning dumping it all in the same bucket. An example of this, if two people want to communicate, we could communicate by just talking, or we could communicate by creating this bucket where we both put messages. The problem with that is, though, what if I take the bucket to put a message in it, and then you try to put a message and the bucket's missing because I have it, right? Not a great way to communicate. All right. What would communicating by sharing memory look like? In addition, why would message passing enthusiasts not use it and do the opposite instead? In a way, channels in any programming language are similar to single ownership, because once you transfer value down a channel, you no longer use that value. Shared memory concurrency is like multiple ownership. Multiple threads can access the same memory location, right? That bucket that we talked about. They can access the same memory location at the same time. So as we saw in the previous chapter, where smart pointers made multiple ownership possible, multiple ownership can add complexity because these different owners need managing. Rust type system and ownership rules greatly assist in getting this management correct. For an example, let's look at mutexes, one of the more common concurrency primitives for shared memory. So again, shared memory, two people want to communicate, they have a bucket where they put messages, but the one person has to take the bucket, put some stuff in it, put it back, the next person can take it. It can cause problems, right? Because I might have the bucket when you're trying to send a message. That we can think of that as shared memory. All right, using mutexes to allow access to data from one thread at a time. Mutex is an abbreviation for mutual exclusion, as in a mutex allows only one thread to access some data at any given time. To access the data in a mutex, a thread must first signal that it wants access by asking to acquire the mutex's lock. So if you want access, you have to say, hey, give me the lock. Let me lock that mutex. Basically what it's saying is, if we're talking about that bucket analogy that we're going to return to a few times, if I'm getting into it, it's like saying, hey, I have the bucket. I'm going to hold it. Everyone chill. I'm putting some messages in. I'll put it back when I'm done, right? So the lock is a data structure that is part of the mutex that keeps track of who currently has exclusive access to the data. Therefore, the mutex is described as guarding the data it holds via the locking system. Dozeboy in the chat says, I remember learning about this at the FLL, the good old days. Ooh, yeah, mutexes. I remember learning about this in school too. It's crazy. All right, mutexes have a reputation for being difficult to use because you have to remember two rules. Front-end lunch and learn. Doze, yes. So I used to teach a front-end lunch and learn. Doze is in the chat. He was part of that. We did a little work session where we taught folks front-end, and now it's evolved. Now we're teaching the whole internet. Let's go, and you're still part of it. Look at this. Evolution. All right, so mutexes, they have a reputation for being difficult. And if you've heard this term, you're probably like, oh, mutexes. And it's because of this reason, right? There's two rules. You must attempt to acquire the lock before using the data. So if you want to get that bucket to put a message in, you must try to get that bucket. And the way you do that is you go to the location where the bucket is stored and you say, oh, can I get this? Otherwise, there might be a message that says Tom currently has it. And then in which case you can't get the lock, right? That's like the analogy. When you're done with the data that the mutex guards, you must unlock the data so other threads can acquire the lock. Basically, when you're done putting your stuff in that bucket, you need to put it back so that other people can get it, right? For a real world metaphor, I already had this metaphor. They're going to come in. They're going to give like the sickest metaphor. Watch this. They're going to blow my metaphor away. Watch, ready? For a real world metaphor for a mutex, imagine a panel discussion at a conference with only one microphone. Before a panelist can speak, they have to ask or signal that they want to use the microphone. When they get the microphone, they can talk for as long as they want to, and then hand the microphone to the next panelist who requests to speak. If a panelist forgets to hand the microphone off when they're finished with it, no one else is able to speak. Yeah, we've all been in that. We've been in that meeting, right? We know one can speak. If management of the shared microphone goes wrong, the panel won't work as planned. So yeah, much better analogy than the bucket, but I like the bucket. I like the bucket analogy. I came up with it. I like it. Management of mutexes can be incredibly tricky to get right, which is why so many people are enthusiastic about channels. They don't want to use mutexes because it's difficult. However, thanks to Rust type system and ownership rules, you can't get locking and unlocking wrong. That's awesome. They're making it so that we can't shoot ourselves in the foot. I love it. I love it. the API of Mutex. So Mutex over the generic T. So we can have a Mutex over generic type. This is powerful. As an example of how to use a Mutex, let's start by using a Mutex in a single threaded context. Let's do it. All right, so we're gonna go ahead and import this here. We're gonna do use standard sync. So it's from the sync library there. We're gonna use Mutex from the standard library. And then we're gonna say let m equal Mutex new. We're gonna give it 5. If we hover and see what this API means, let me just put a semicolon here. We see that Mutex new can create a generic T, creates a new Mutex and unlock state ready for use. And so here I'm passing it an I32. And you can see here, our Mutex is generic over the type integer 32. Let me zoom in one level to make it a little bit better. There we go. Okay, so what are we gonna do next? We're gonna create a scope, right? That's what our block is gonna do there. And we're gonna do let mutable number equal m.lock, grabbing that lock, dot unwrap. And you can see we have a Mutex guard, which is what the lock returns, a Mutex guard, generic over the signed 32-bit integer. And what are we gonna do? We're gonna change it because it's mutable. So we're gonna say num equals 6. And so here we're dereferencing number, getting the value. So we have to dereference it, meaning I guess the Mutex has a deref. It implements the deref trait. So we're going to dereference it and set it equal to 6. And then down here, we're going to print m equals, and we're going to use that debug trait, right? That's how we're going to print that, m. All right, let's run it. Clear this out, move this up, get out of your way, and run it. So we see m equals Mutex data 6. So it shows you that the Mutex contains the data. What data? 6. So this deref here, the deref trait they've implemented mutates the data within the Mutex. That's why we use the deref, right? It's not just storing the value 6, it's storing the value 6 as data, and that's why they give you the deref API to set it. Makes sense. We learned about that 2 chapters ago. Okay. As with many types, we create a Mutex using the associated function new. To access the data inside the Mutex, we must use the lock method to acquire the lock. This call will block the current thread, so it can't do any work until it's our turn to have the lock. Clam Watson in the chat, what up? The call to lock would fail if another thread holding the lock panicked. Okay, that's key. That's important, right? And that's going to help us a lot, because that's one of the problems in other languages is when something has a lock and that thing that's holding the lock dies or disappears and you can't get the lock. That's like someone coming and taking that bucket, or in their analogy, the microphone, just leaving the venue, right? No one can get that mic back. But in this case, if that thing panics, the lock will fail. So if there's an issue with the thread, the lock will fail. In any case, no one would ever be able to get the lock, so we've chosen to unwrap and have this thread panic if we're in that situation. So that's why we used unwrap. After we've acquired the lock, we can treat the return value, named num in this case, as a mutable reference to the data inside. The type system ensures that we acquire a lock before using the value in Mutex, so in that m. So we have to get the lock before using the value, is not an integer 32. So we must acquire the lock to be able to use the 32-bit integer. We can't forget the type system won't let us access the inner 32-bit integer otherwise, and that's this here, right? We're not just accessing, we have to use the deref trait, we have to dereference it to get access to that value. And we also need to acquire this lock before we can access this. Pretty cool. As you might suspect, Mutex over the generic T is a smart pointer. Yeah, that's what I'm saying. That's why we have that deref trait implemented, right? More accurately, the call to lock returns a smart pointer called Mutex guard, wrapped in a lock result that we handle with the call to unwrap. So lock here returns a result. And you may remember, unwrap tries to take a result and get the value out. If it fails, it will panic. If it succeeds, you'll simply get the value. So unwrap is basically shorthand for doing a case statement, right? On a result where you say, okay, give me the value, error, do something else. it's also similar to using the question mark. Unwrap just says, get me the value if it's there, otherwise panic. And so that's the benefit of using unwrap with lock, is you guarantee that if this thing panics, the lock will fail. All right, so it's wrapped in a lock result that we handle with the call to unwrap. The mutex guard smart pointer implements deref. Yeah, we're way ahead. Look at this. To point at our inner data. The smart pointer also has a drop implementation that releases the lock automatically when a mutex guard goes out of scope. When did this mutex guard go out of scope? Well, this mutex guard went out of scope as soon as line 8 finished executing, right? Because it's block scoped. So once it reaches this, it's no longer in scope. Cool? All right. So the drop trait is called, which releases the lock. It happens at the end of the inner scope that we see there. As a result, we don't risk forgetting to release the lock and blocking the mutex from being used by other threads because the lock release happens automatically. That's really cool. So we got the lock, we leveraged it to mutate the data, and we let the scope drop the lock, right? After dropping the lock, we can print the mutex value and see that we're able to change the signed 32-bit integer to 6. And we saw that, right? It printed out 6. Very cool. Sharing a mutex between multiple threads. We saw sharing state between threads before, right? With the move. Now let's see how we can do it with mutex. Now, let's try to share value between multiple threads using mutex. We'll spin up 10 threads and have them each increment a counter value by 1. So the counter goes from 0 to 10. We're going to have 10 threads, each incrementing by 1, should go from 0 to 10. The next example in listing 1613 will have a compiler error, and we'll use that error to learn more about using mutex and how Rust helps us use it correctly. All right, so we're deliberately going to have an error here so we can learn a little bit. Why? Because our compiler output shows us amazing errors. All right, so let's do this. I'm going to go ahead and comment this out. I'm just going to put a comment here. An example of a single threaded. Okay, so let's see what we got here. We're going to pull in thread because we're going to create, remember, 10 threads. And we're going to do let counter equal mutex. We're going to start it out with state. It's going to have a signed 32-bit integer starting at 0. Handles equals vector. We're going to use that vector macro to create the vector instead of using vector new. And then we're going to iterate over it for, we don't care about the number itself. So it's just 10 iterations. That's why we're using the underscore. We're going to create a range to 10, and we're going to say let handle equal thread. We're going to spawn a new thread. We learned about this last week. We're going to move into that closure so that the closure takes ownership, right? That's what that's doing there. Let mute number, so we're going to declare number as mutable, and we're going to do counter.lock. So we're going to grab a lock on that. And remember, counter is a mutex, so we can successfully grab a lock on a mutex. Then we're going to go ahead and dereference number so that we can access and mutate the value. And we're going to set the value equal to itself plus 1. That's what the plus equal does. So this is equivalent to this, right? It's just shorthand. Okay, and then what we're going to do is we're going to do handles.push handle. So we're putting this handle here, we're going to put that onto our handles vector up here. We're just pushing it on there. And then we're going to iterate over those handles. So for handle in handles, we're going to do handle.join unwrap to get those values out. And then down here, we're going to do print ln. Oh, sorry. Oh, fast figuring that. Result. And our result, we're going to dereference counter.lock. Again, we got to grab, if we want to grab the value, right, we have to grab a lock to it and unwrap it. And we're going to dereference it to get the value, because otherwise we'd see what the whole counter was, and it would be a mutex with a data attribute. We want to just get the value from that data, so we use our deref. And why can we use that? Well, because counter lock returns a smart pointer that implements the deref trait. Okay, let's go over it one more time. We have our counter. Oh, let's just read they're going to go over it right here. Let's just read that. Not that I couldn't do it though. You know what I'm saying? We create a counter variable to hold a signed 32-bit integer inside of mutex t. Next, we create 10 threads by iterating over a range of numbers. That's what this does. So again, we don't care about this. We use an underscore. We just want a loop of length 10. We use thread spawn and give all the threads the same closure, one that moves the counter into the thread, acquires a lock on the mutex by calling the lock method, and then adds 1 to the value in the mutex. When a thread finishes running its closure, num will go out of scope and release the lock so another thread can acquire it. So this is our scope here. By this line, it is unlocked and released it so that another one can handle it, right? In the main thread, we collect all the join handles. That's what we're doing here by pushing them onto the handles vector. Then, as we did in 16.2, we call join on each handle to make sure all the threads finish. At that point, the main thread will acquire the lock and print the result of the program. We hinted that this example won't compile. Let's find out why. So let's run it ourselves here. And so we see here, because we get this nice little colored output here, move occurs because counter has, so used of moved value counter, so counter was moved. Move occurs because counter has type standard sync mutex, which does not implement the copy trait. So we know that a function can take ownership of it. So the value moved into the closure here. So we moved counter into this closure when we declared this closure with move. And we could have seen this error by just hovering over here, right? Which is pretty awesome about Rust Analyzer. Okay. Use occurs due to the use in the closure. So then we try to use it here, right? We try to use it here, then it's been moved. And so it aborts. And so here we can read their take on that. So the error message states that counter value was moved in the previous iteration of the loop. So Rust is telling us that we can't move the ownership of lock counter into multiple threads. Let's fix the compiler error with a multiple ownership method we discussed in chapter 15. We're about to use the ref cell. I know it. Reference counting. Let's go. Let's check it out. In chapter 15, we gave a value multiple owners by using the smart pointer reference counter to create a reference counted value. Let's do the same here and see what happens. We'll wrap the mutex in a reference counter and clone the reference counter before moving ownership to the thread. Now that we've seen the errors, we also switch back to using the for loop and we'll keep the move keyword with the closure. Okay, so what are we doing here? We're gonna, instead of just creating this mutex, we're gonna create a reference counter. Okay, and I'll go over, don't worry, I'll go over what this does again. We'll do a little quick recap. And we have our loop. And so first, before handle, they're gonna create a clone. So we're gonna say counter equals reference counter clone, and we're gonna clone counter. All right. And then we have handle thread spawn move counter.lock. Okay, what is this saying here? Use of move value counter, value moved into closure here in previous iteration of loop. Okay, that's okay. It's because we have to first pull in our C. So we're going to pull in our reference counter. Now here we have thread spawn. Cannot be sent between threads safely. So it's saying it cannot be sent between threads safely. Let's see. Let handle thread spawn move. So here we get this error. Once again, we can't compile. We get different errors. The compile is teaching us a lot. So it says here, a reference counter mutex cannot be sent between threads safely. Interesting. Wow, that error message is very wordy. Here's the important part to focus on. Reference counter mutex cannot be sent between threads safely. The compiler is also telling us the reason why. The trait send is not implemented for a reference count mutex. If you remember the trait send we learned about in chapter 15. We'll talk about send in the next section. It's one of the traits that ensures the types we use with threads are meant for use in concurrent situations. Unfortunately, reference counter is not safe to share across threads. When reference counter manages the reference count, it adds to the count for each call to clone and subtracts from the count when the clone is dropped. But it doesn't use any concurrency primitives to make sure that the changes to the count can't be interrupted by another thread. This would lead to wrong counts, subtle bugs that could in turn lead to memory leaks or value being dropped before we're done with it. What we'll need is a type exactly like reference counting, but one that makes changes to the reference count in a thread-safe way. Okay, let's dive into that a little bit because it's a little bit of chapter 15 recap, right? So a reference counter. A reference counter keeps track of remember we said it's indirection around a value. What it does, it creates extra smart pointers because it's a smart pointer. It creates extra smart pointers to the same value. So for example, what I mean by indirection is imagine this cup. And Dozeboy and Albert, if you're in the chat, you'll recognize this water bottle as a former employee of ours. So we have this bottle. This is the bottle itself. To add a layer of indirection, we can create a pointer to the bottle. So the indirection is when you want to get to the bottle, you first go to the pointer that then directs you to the bottle. So that's a layer of indirection, right? You get to the pointer points to the bottle. A reference counter allows you to create multiple indirections or multiple pointers. So instead of just having one pointer to it, I'm going to hold it here, I can have two. And the way I do that is I wrap the thing, right? I wrap this thing in a reference counter, and then I clone the reference counter. Now I have 2 pointers. So basically you're dealing with the same data, but you, instead of giving ownership, when I pass it to a function, instead of giving the function ownership to this thing, I give the function ownership to the pointer. So that's the layer of indirection, and that's how they work and give us the benefit of allowing for multiple owners of the same data, because those owners simply just own that indirection, they own that pointer. So what it's saying here is the problem with that, right? The problem with that is a reference counter, while we can create clones and create pointers, we're still dealing with mutexes. And we're dealing with threads that can operate on something at a different time. Or, right, they could try to operate on something at the same time. So the problem there is, what if the person that owns this pointer tries to change that? And the person that owns this pointer tries to change it at the same time. They don't know that this one's trying to change it. All they know is this thing tries to grab a lock. But again, they're getting a lock on the pointer, not on the value. So they have a lock on this pointer, great. This person can still try to deal with it, right? So it's not thread safe. And so we're going to find out a thread safe way. And it looks like the thread safe way is arc. Arc, that's a cool word. All right, so let's go more in. Hopefully that made a little sense. Atomic reference counting. We may have heard this term before. It sounds familiar to me. Fortunately, atomic reference counting is a type like reference counting that is safe to use in concurrent situations. The A stands for atomic, which is it's a cool word, meaning it is atomically reference counted type. It's an atomically reference counted type. Atomics are an additional kind of concurrency primitive that we won't cover in detail here. See the standard library documentation for more details. At this point, all we need to know is that atomics work like primitive types, but are safe to share across threads. Pretty cool. You might then wonder why all primitive types aren't atomic and why standard library types aren't implemented to use atomic types by default. I bet it's a performance thing. We'll find out. The reason that thread safety comes with... Yo, I didn't read ahead. You're all thinking, you're like, Tom, you read ahead. The word was right underneath it. You saw it. I didn't. I just knew. I'm a station. The reason that thread safety comes with a performance penalty that you only want to pay for when you really need it. If you're just performing operations on values within a single thread, your code can run faster if it doesn't have to enforce the guarantees atomics provide. Makes sense. You want that extra feature, you got to pay a little more, right? You want to be able to simulcast to YouTube and Twitch, you got to pay for the Streamlabs Pro, you know? Let's return to our example. Arc and reference counting have the same API, so we could just fix it by adding a I guess, at the beginning. Yeah, we just fix the program by changing the use line to call, and the call to new, and the call to clone. Let's do it. So arc comes from mutex, so we can pull that in. Remember, we can pull that in by doing this syntax. That means we're pulling 2 things from the same library. If you are familiar with JavaScript, that's something like import arc mutex, right? From standard /sync maybe, right? Or if you're coming from Python, something like from standard sync import arc, or in this case, I guess it'd be arc, comma, mutex, right? Same thing. We learned about that, shorthand. And we can get rid of our reference counting. We're no longer gonna need it. It's not doing what we need it to do. So we're just gonna go ahead and get rid of it. Okay, and we just change our RC, right? Arc, for some reason my multi-cursor is not working. So I'll just do it like this. And we just need new and our clone. Where's our clone? There's our clone, there's our new, there's our import. All right. No complaints from Rust Analyzer. Let's try it out. Let me get out of your way. Let's run it. Bam, result 10. It worked. Pretty cool. I like it. All right, the code will print the following. We did it. We counted from 0 to 10, which may not seem very impressive. It's not. It's not impressive. To be honest, it's not. It's not impressive. But it is impressive that we use mutexes for it. It taught us about mutex and thread safety. You could also use this program structure to do more complicated operations than just incrementing a counter. Using this strategy, you can divide a calculation into independent parts, split those parts across threads, and then use a mutex t to have each thread update the final result with its part. Pretty cool. Pretty cool, right? All right, similarities between refcell-t, reference counting, and mutex arc. So remember refcell? So it's saying that there's similarities between refcell's relationship to reference counting and mutex's relationship to arc. You might have noticed that counter is immutable, but we could get a mutable reference to the value inside it. This means mutex t provides interior mutability. We saw that, right? That's what the deref, that's this. This is interior mutability. We are able to mutate it using the dereference. And that's why, remember, if we printed out mutex guard, we saw that it had a data property, and the data property had the value. But this interior mutability allowed us to mutate it, right? So the cell family did the same thing. In the same way we use refcell in chapter 15 to allow us to mutate contents inside of reference counter, we use mutex to mutate contents inside of an atomic reference counter. Another detail to note is that Rust can't protect you from all kinds of logic errors when you use mutex. Recall in chapter 15 that using reference counter came with the risk of creating reference cycles when two reference counter values refer to each other, causing memory leaks. Similarly, mutex comes with the risk of creating deadlocks. It's the infamous word that's always follows mutex. These occur when an operation needs to lock two resources and two threads have each acquired one of the locks, causing them to wait for each other forever. So let's go over that again. This occurs when an operation needs to lock two resources and two threads have each acquired one of the locks. So thread A needs access to the water bottle and the remote. And thread B needs access to the water bottle and the remote, but this one's holding this one and this one's holding this one. That's a deadlock. This one's waiting for the water bottle and this one's waiting for the remote. So they're deadlocked. This one doesn't want to give it up because it needs both, and the other is this one. It's like one of those situations where like, no, I need that. You know, deadlock. It also sounds like a cool video game name or something. All right, the standard library API. Oh wait, missed a part. If you're interested in deadlocks, try creating a Rust program that has a deadlock. Then research deadlock mitigation strategies for mutexes in any language and have a go at implementing them in Rust. The standard library API documentation for Mutex and Mutex Guard offers useful information. Maybe we'll do that. We'll come back to that. We'll round out this chapter by talking about the send and sync traits and how we can use them with custom types. All right. Extensible concurrency with send and sync traits. So let's see, are we writing any code? No, we're not writing any code. So we'll just read through it and then we'll see where we go from there. Extensible concurrency with the sync and send traits. Interestingly, let's pull this up here. Interestingly, the Rust language has very few concurrency features. Almost every concurrency feature we talked about so far in this chapter has been part of the standard library, not the language, right? We're all importing it from the standard library. Check it out, right? Pretty cool. Your options for handling concurrency are not limited to the language or the standard library. You can write your own concurrency features and use those written by others. However, two concurrency concepts are embedded in the language: the standard marker traits, sync and send. So the standard marker traits, sync and send, are built into the language itself, allowing transference of ownership between threads with send. The send marker trait indicates that ownership of the type implementing send can be transferred between threads. Almost every Rust type is send, but there are some exceptions, including reference count, that cannot be sent because if you clone the reference counter value and try to transfer ownership of the clone to another thread, both threads might update the reference count at the same time. Because remember, every time you create a pointer, remember the water ball? Every time you create a clone, that reference count has a count to the number of clones that are out there. And if you pass that around, you can mess up the value, right, of that count. That count needs to work, right? Again, so if you clone the reference counter value and try to transfer ownership to another thread, both threads might update the reference count at the same time. For this reason, reference count is implemented for use in single-threaded situations where you don't want to pay for the thread-safe performance penalty that something like atomic reference counting gives you. Therefore, Rust type system and trait bounds ensure that you can never accidentally send a reference counter value across threads unsafely. When we tried to do it before, we got an error. The trait send is not implemented for reference counting of the mutex. When we switch to arc, which is send, right, it has that send trait, the code compiled. Any type composed entirely of send types is automatically marked as send as well. So if a type is composed of types and every type it's composed of is marked as send, then the type itself is send. Almost all primitive types are send, aside from raw pointers, which we'll discuss in chapter 19. Allowing access for multiple threads with sync. The sync marker trait indicates that it is safe for type implementing sync. So the sync marker trait indicates that it is safe for the type implementing sync to be referenced for multiple threads. So if something is sync, it can be referenced for multiple threads. In other words, any type T is sync if the reference to T is send. Let's go over that again. Any type T, any generic type T is sync if the reference to it is send, right? If the reference to T can be used across threads, then T is sync, meaning the reference can be safely sent to another thread. Similarly, send primitive types are sync, and types composed entirely of types that are sync are also sync, so similar to send. The smart pointer reference counting T is also not sync, so we know it's not send, but it's also not sync, and it's for the same reason. The ref cell type, which we talked about in the previous chapter, and the family of related cells types are not sync. The implementation of borrow checking that ref cell does at runtime is not thread safe. The smart pointer mutex is sync and can be used to share access with multiple threads, as you saw in sharing a mutex between multiple threads section. We just did that. Implementing send and sync manually is unsafe. Because types that are made up of send and sync traits are automatically also send and sync, we don't have to implement those traits manually. As marker traits, they don't even have any methods to implement. They're just useful for enforcing invariants related to concurrency. Manually implementing these traits involves implementing unsafe Rust code. We'll talk about using unsafe Rust code in chapter 19. For now, the important information is that building new concurrent types not made up of send and sync parts require careful thought to uphold the safety guarantees. The Rustonomicon, cool book name, has information about these guarantees and how to uphold them. All right, summary. This isn't the last you'll see of concurrency in this book. I'm excited. In chapter 20, we will use the concept in this chapter in a more realistic situation than the smaller examples discussed here. Spoiler alert, in chapter 20, we build a multi-threaded web server. I'm pretty excited about it. It should be fun. It's going to be a real project. We're going to use all the stuff we've learned, right? So that's going to be awesome. That's what they're talking about here. As mentioned earlier, because very little of how Rust handles concurrency is part of the language, many concurrency solutions are implemented as crates, right? The external crates. These evolve more quickly than the standard library, so be sure to search online for the current state-of-the-art crates to use in multi-threaded situations. The Rust standard library provides channels for message passing and smart pointer types, such as Mutex and arc, that are safe to use in concurrent contexts. The type system and the borrow checker ensure that the code using these solutions won't end up with data erases or invalid references. Once you get your code to compile, you can rest assured that it will happily run on multiple threads without the kinds of hard to track down bugs common in other languages. Concurrent programming is no longer a concept to be afraid of. Go forth and make your programs concurrent fearlessly. That's awesome. Next, we'll talk about idiomatic ways to model problems and structure solutions as your Rust programs get bigger. In addition, we'll discuss how Rust idioms relate to those you might be familiar with from object-oriented programming. We did some functional, about to get into some object-oriented, all before 10 p.m. All right, that wraps it up for Chapter 16, Concurrency.